Okay, let's cover tea. 8.2 is a bit tedious looking ahead, so I'm going to split it up into 3 parts. So you've got part A, part B, determine the percentage error introduced in the computation by assuming that the bar is straight. And then you've got consider the case where RL is 20 millimeters, 202 meters. So to me, that there's actually, this is a separate part. You want to consider. So I'm going to probably split this video up into 3. So look at part A, B, this assumption that it's a straight bar, and then we're looking at the various cases. Right. Need a few more of these. Let's go back. Okay, so let's make a start. So so looking at part A here, we have been given the radius of 15 millimeters. So for this case, determine the largest tensile and compressive stresses. Notice you've got a pure turning moment here. Right, so look at the units. First of all, it looks like that you've got a downward force, but no, you don't. You've just got a turning moment. So you're trying to bend this thing towards that side and then pull it out on the outer side. So I don't have to worry about any sort of compressive or tensile forces or other bending forces other than this M equals 120 Newton meter term. How am I going to approach these problems? Let's kind of go through the approach that we did last time. So let's start with what we did up here. So the centroid is going to be what? 15 plus half of 40, so that's 20. So we've got a centroid at 35 millimeters. The R values that we're interested in is the inner, so that'd be 15 millimeters, and the outer, so that'd be 15 plus 40, 55 millimeters. So the inner one should be in compression and the outer one should be in tension. What else did we do? Well, you can work out the area. Just do basic stuff for the moment. So the cross-sectional area of this is 40 times 60. Okay, 4 times 6. Right. And it's a standard centroid thing, so we could use a standard result or solve it ourselves for the neutral axis. So recalling I use the equation. I don't have a lookup table. So we need to solve that. So the area I found, I'm going to be integrating with slices going like this, outwards. My R's pointing outwards there, so that becomes the width, as it were, is this height. So that's 60 times delta R over R. Start location will be 15 and end 55. Right, so let's solve that. 60 into 2,400 becomes back down to 40. Integrate the 1 over R. So that would be natural log 55 over 15. So neutral axis is 40 divided by natural log 55 divided by 15. So that's 30.786 millimeters. Right, what else am I going to do? So I think that's it. So now let's just use my stress equation. Only doing part A at the moment. So I'm going to use this equation here. Stress equals M over A So that's the equation we're going to use for that. M is just going to be the 120. R's going to have two different values to plug in. Everything else is dandy. Might as well just put my numbers in twice. So inner 120. I'll work in millimeters. It's 15. Take away R. The area is 2,400. Centroid is 35. And there's the inner, so it's 15. So I need to work that out. And I am getting not the right answer. Okay, I've introduced an error because of my units trying to be clever, working in millimeters. So let's do this again in SI units. So that's times 10 to the minus 3. What we've got here. Times 10 to the minus 6 to the minus 9 to the minus 12. Okay, so meters, 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 meters. So 10 times 10 to the minus 12. That's in Newton meters. So my answer now is going to be in SI units. Okay, there we go. No cheating. Pascals. Okay, that's what I'm looking for. And then for the outer, same thing, just different numbers. A bit tedious. 55 this time. Convert that to SI units. So lesson learned here, be careful when you have introduced a different unit there. I could have converted that, I suppose, into millimeters and then got the answer into the megapascals. .55 there times 10 to the minus 12 there. So this case, 120 times 55, 2.76 that. Doesn't close my brackets properly. Okay, open a bracket, close it, open a bracket, close it, close it. Right, finally. Tempting to, when you do your calcs, I think, tempting to leave these things out and put them in at the end. Anyway, hinge, so this time I've got, there we go, 5 5.2237. Okay, so stop this one here, and we've done up to part A.